So, good evening, everyone. I welcome you all to Analog Electronic Circuits live problem solving session. I am Dishada Devi and PMRF Fellow from IIT Gandhinagar. So, today we'll be moving to week 4 problems. So, hope I'm audible clearly. If somebody could confirm, am I audible clearly?
Yes, ma'am.
Hello? Okay, so you people can unmute yourself and answer. Just in case if you have any doubts or any queries, please feel free to unmute yourself and answer and question also. So we'll moving to week 4 problem solving sessions. In this week, we'll be solving all different types of amplifier configurations, and we'll see basically whatever we understood last time. We'll try to implement those, and also we'll look into what are the behaviors, that basic properties that we have with different types of amplifiers, that will also we'll see. So in this first problem, uh, there is this amplifier. So first of all, what type of configuration is this? What configuration is this? What type of MOSFET is that? Is it a PMOS or an NMOS?
PMOS.
Yes, is it a PMOS or an NMOS?
PMOS.
Okay, so yeah, maybe Mallikarjun, if you can unmute and answer. So, what is this type? What is the MOSFET? What is this MOSFET? Is it a PMOS or an NMOS?
Ma'am, it is PMOS.
And also, what type of biasing? What type of amplifier is this?
Common gate.
Yes.
Common gate, ma'am.
Common source.
Okay, so maybe I'll answer for this. So this is a PMOS. How do you know it is a PMOS? Because current is going inside the terminal. So if current goes inside the terminal, then it is a PMOS. If current comes out of the terminal, then it is an NMOS. We discussed it before last week. And now, since it is a PMOS, we know in PMOS the source terminal is at higher bias or higher potential compared to the drain terminal, and this is gate terminal. Now, since we can clearly observe that the input has been given to gate and output is taken from drain, so this is a CS amplifier, correct? So, in this CS amplifier, so first of all, for an amplifier operation, the MOSFET needs to be in saturation. So PMOS in saturation. So we know that for current equation, we need to apply the saturation current equation. Now it is given that kW by L is 0.5 milliampere per volt square, and VTHP is minus 1 volts with lambda equal to 0 volt inverse. We discussed about lambda as well in the last class, so which is channel length modulation factor. Now the question is, you have to calculate the operating point. So operating point can also be termed as biasing point, okay, or DC point. So all of these mean the same. So basically you have to find the DC values for source drain voltage and drain current. Now, with these values given, and we know that the transistor is in saturation, so we can write the current equation as kW by 2L VSG, because it is a PMOS, mod VTH P whole square. So we have ID as 0.5 by 2 into, what is the value of VSG over here? So we see that yeah. So here we know that VSG basically means Vs minus Vg. Now here Vg would be how much? So we see that there are two resistors of 20 kilo ohm, 20 kilo ohm, and 8 volts is being distributed among them. So now since it is a DC bias, so this capacitor is open circuit. So this particular resistor will not be considered. So that's why from this 20 kilo ohms to 20 kilo ohms, we get VG as 4 volts. And if we take a KVL across this from VDD to ground, so VDD can be written as VSD minus ID into RD. And Vs is actually
VS is 8 volt, right?
VSD minus ID into RD. Now, if we look into this, so this is not required basically. If we look into this particular terminal, so this is the source terminal, right? And source is directly connected to VDD. So, in case of VDD connection, or basically in case of voltage source connection, the voltage at that particular terminal is directly equal to either ground or if the voltage source is connected to it. So basically Vs will become 8 volts. So with this, our VSG becomes 8 minus 4, that is 4 volts. So ID will become 4 minus mod of minus 1 whole square. So this is ID equal to 0.5 by 2 into minus 1, right? Yeah. So 9.5 by 2 into 9. So that is 2.25 milliamperes. So the current across the MOS transistor is 2.25 milliamperes. Now, in case of VSD, which was asked next, VXT can be written as VDD plus IDRD. So VSD is 8 plus okay, so here it is not VSD because VSD is at the end the same thing. So here it will be like VS is already VDD, right? And VD is ID into RD, that is also known. So if we want to find VSD, so this will basically become VDD minus ID into RD. So here it is 8 minus 2.25 into 2 kilo ohms. So this will be 4.5. So VSD Q will be 3.5 volts. And also this DC operating point is also known as Q point also. So if you are asked to find the Q point, then also it's the same thing. You have to find the DC operating point. So biasing point, operating point, DC point, Q point, all of them refer to the same thing. Okay. Now, if we move on to the next problem. So in this problem, we have to calculate the small signal gain AV for the circuit shown above. Consider that coupling capacitor C1 is shorted for the input signal. So, for this particular circuit, the best way to find the gain, small signal gain, is to draw the small signal model of this particular circuit. So the small signal model will look like, hello, am I audible?
Yes, ma'am.
Students, am I audible? But I guess the screen is stuck, right? Are you able to see my scribblings? Oh, okay. Are you able to see what I'm writing? Okay, yeah, so there is some lag because of which I could not see anything on my screen. But yeah, anyways, so I guess there is again some network issue. On the output side will be like this, and this will be GM VSG. This is source, gate, drain. Here plus minus VSG. So this is the internal diagram of the small signal model. Since lambda is already 0, so we don't have to consider the R0. Now we have, this will go to AC ground. Yes, this will go to AC ground. This is shorted, and we will have input is going from, okay, since this is grounded, so let's ground this, and input is connected, let's say, between ground and VG. So this is VN with a resistor of 10 kilo ohms. Then between ground and gate, we have two resistors, these 20 ohms, 20 kilo ohm, R1 and R2. So these two will also come here in parallel. So R1, R2, and there is another resistor which is connected between drain and ground. So this is RD. You can connect it like other way around also. This is also fine, and this will be V out. So basically this potential will be V out. So we can clearly see that V out is actually whatever is the current flowing through RD, IRD into RD, correct? Now, if we see from this diagram itself, it is clearly visible that this IRD is actually this GM-VSG, correct? So now V out is GM into VSG into RD. Now the question is, we want to find V out upon Vn. So Vn will come as a function of VSG or vice versa. So these two are function of each other, right? So now let's see. See, Vn is actually not equal to VSG. Why? Because there is this 10 kilo ohm resistor here at the gate. So it is basically like there is this Vn 10 kilo ohm resistor, and then there is this parallel combination R1 parallel R2, and this is where you will find VSG. So from this diagram, we clearly know that VSG is R1 parallel R2 upon R1 parallel R2 plus 10K into Vn. So this is what is VSG. So this can be drawn here, or RD can be drawn like this as well. So this is the same RD, and again from here this is V out, and whatever is current flowing through will be this VSG. So yeah, now V out can be written as GM into R1 parallel R2 upon R1 parallel R2 plus 10K into Vn. So V out by Vn, that is the gain, will be equal to GM R1 parallel R2 upon R1 parallel R2 plus 10K. Now since we know this V out, we can simply substitute the values and we'll finally find the answers. So here we need to find, we know R1, R2 and K, but we don't know GM, right? So we'll find GM first. Yeah. So first of all, let's find GM. So how do we find GM? GM is KW by L VSG minus VDHP mod, correct? From the formula. So this will be 0.5 into 4 minus 1. So that is 3. So GM is 1.5 millisiemens. Now we know GM, we know R1 parallel R2 will give us, so this is 20 kilo ohm parallel to 20 kilo ohm will give us 10 kilo ohms. So V out by Vn will be 1.5 millisiemens into R1 parallel R2, that is 10 kilo ohms, upon R1 parallel R2, that is 10 kilo ohms, plus 10 kilo ohms into RD also, right? So here there was this RD as well from here. So into RD was 2 kilo ohms. So V out upon V in is 1.5. 1.5 volt by volt. So the gain in volt by volt is 1.5, whereas when we have to find the voltage gain in dBs, this will become 10 log 1.5, which is 1.76 dBs. Okay, so this is the solution. Now moving on to question number 3. So in this particular question, we have to find the input resistance seen from the signal source for the circuit shown. So here basically it is again the same circuit, but here we have to find the input resistance observed by this particular signal source. So what are the resistors that this particular source will observe? So if we look from here, we'll see the structure is somewhat like this, correct? So we have seen this in our small signal model also. This is 10K, 20K parallel to 20K. This is ground. So this is Zn. So Zn is 10 kilo ohms in series with 20 kilo ohm parallel to 20 kilo ohm. So Zn is 20 kilo ohms. Is this clear to everyone? How we found out the input resistance? Any doubts in the input resistance?
No, ma'am.
Okay, so I hope this is clear. If you have any doubt, please unmute yourself and ask. So meanwhile, moving on to the next problem. So in this problem, now what type of MOSFET is this? And what is the amplifier configuration here?
NMOS and common source.
Yes, what type of MOSFET is this? And what is the amplifier configuration here?
NMOS.
Sorry, I did take. Oh, I took 20 log, right? Yeah. For this, it would be 20. Okay, so with 20 log, because so it is voltage gain, so it would be 20 log, and the value is 3.5 dBs, 3.52 dBs. So the voltage gain is 3.52 dBs, and yes, it should be 20. So you people are not unmute, so that is the reason you have to unmute your mic.
Hello, can you hear
If you
me?
can speak something.
Yeah,
Hello.
I'm. Uh,
Hello.
Yeah, we are trying to speak, but I think you're not able to hear
So
us.
you people are unable to. So you people are not audible to me. That is correct. But why is this so?
Hello.
Yeah,
Hello,
yeah.
ma'am.
Yes, now you are audible.
Okay, ma'am.
Yeah, yeah. So that's why. So there was some. You have to unmute yourself. Then you will be audible. I'm
Ma'am.
audible to you clearly, right? So basically,
Yes,
there
ma'am.
were some glitches where I was like my screen was stuck completely, and whatever I was writing, I could not see it on my screen itself. So that's why I was confirming that. Yeah, nice. So in this particular problem, what type of MOSFET is this? And what is the configuration of the amplifier?
Ma'am, it is an NMOS
NMOS and common
Yes.
source.
common source.
Again, NMOS with CS amplifier. So in this particular problem, again kW by L is given 1 milliampere volt square. VTH is 1 volt. And again lambda is 0 volt inverse. R1 is given as 60 kilo ohms. This is 60K. This is 20K. And RD is given as 2K. VDD is 12 volts. Yeah. So in this problem, what you have to find is again the small signal voltage gain for the circuit shown, and assume the signal coupling capacitor is shorted for the input signal given. So here also, so here we know that for the CS amplifier, the gain is GMRD. So it is very easy to observe from even your small signal model as well. So if this is gate, this is drain, this is source. So source is grounded, and from gate you are giving your input. This is Vn. Here you have R1 parallel R2 parallel plus minus VGS. From here we have GM VGS, and here there will be RD. This is V out. So again, V out is whatever voltage drop across RD will be V out. So IRD into RD. Here RD will be minus. So IRD will be minus of GM VGS, considering that this particular GM VGS circulates through the this part of the circuit. So it will be minus GMVGS because the current is going from downwards and you are seeing the voltage from up to down. So that's why the negative into RD. And again, here VGS is Vin. In this particular case, VGS is Vin. So V out by Vn is minus GMRD. Now we know so first of all, we know the RD, we need to find the GM. So what is the formula for GM? GM is KW by L, VGS minus VTH. So we need to find this VGS. So VGS can be found out as KW by L VDD into 20 upon 20 plus 60. Since S is ground, so no need, minus 1. So this will be, in place of VDD we have 12 volts. So this is 1 milliamps volt square per volt square into 12 upon 1 by 4 minus 1. So this is 3 minus 1 2. So your GM turns out to be 2 millisiemens. RD is 2 kilo ohms. So V out by V in becomes 4 volt by volt. So this is clear, right? And when we go for its dB gain, so it is 20 log 4 so this is 12.04 dBs. Right? Okay, so moving on to the next problem. This was question number 4. So question number 5. In the same problem, again we have to find the input input resistance. So what will be the input resistance for this particular circuit seen from the input resistance seen by this input source? Yes, what will be the input resistance?
That is 60 parallel 20.
60 parallel
K.
20, right? So Zn will be 60K parallel 20K parallel infinity of K. So it will give us Zn of 15 kilo ohms. Yeah. So moving on to the next problem, question number 6. So in this problem, you have to find the output resistance for the circuit given. Now, since here again lambda was 0, so we don't have to consider R0. That means what will be the output resistance observed here? So from when you consider the output resistance, so it is, yes, so you can simply go
RD.
to the small signal model, and from small signal model, if you'll analyze, so it will be very easy. So here the Z out will be simply the RD, which is 2K. But if there was R naught present, so it would have been RD into R naught, okay? So please keep this in mind. That is important. Yeah, please unmute yourself. Yes.
With R naught present, should it not be RD parallel R naught?
Oh, yeah, RD parallel R naught. So they will come in parallel, both of them.
Thank you.
Yeah. RD into R naught. No. RD parallel R naught. Yes. Because they will come in parallel. So it's simply, so it's more like how, so when you simplify your circuit into the small signal model, so it's very easy to analyze the things further, because all of these are very evident from that small signal model, and it's also very easy to analyze the small signal model. That's why small signal models are formed. So there you can simply connect all the resistors the way they look in the circuit, and there you can analyze them properly. So it will give you a better understanding of the circuit. Now, moving to the next problem. So in this problem, we have to find the value of signal coupling capacitor C1 such that the lower cutoff frequency of the amplifier in this, again the same figure, is 10 Hertz. We have to find the value of this capacitor. So we know frequency, right? Frequency is 1 upon 2 pi RC. Now here basically this R will be Rn and the C is C1 or Cin over here. So 10 Hertz should be equal to 1 upon 2 pi Rin, that is Zn, which was 15 kilo ohms earlier, into C1. So C1 is 1 upon 2 pi into 15 kilo ohms into 10. So C1 is almost approximately 1 microfarad. Okay. Now the next problem, we have find the power dissipation for the amplifier again, uh, including the biasing circuit as shown in this figure. So select the correct options. So when we say power dissipation, so power should be from, so power will be VDD into whatever current is flowing here. So let's say I write it as IDD, okay? IDD. So this is the power dissipation of the whole circuit. Now this IDD, if you look at this, there are two branches that are coming out of this IDD. One is this branch, which is the MOSFET current, that is ID. Plus there is this another current, say I1, which is going through this biasing circuit, plus I1, right? ID we have already found out how much was that earlier. We didn't find out ID. Okay, we did not find ID here. So maybe we can simply find ID. That is KW by 2L VGS minus VTH whole square. So this will be 1 by 2 into VGS was, how much was the VGS? It was, okay, so here we need to find the VGS from here. So this will be 12 into 20 by 20 plus 60. So that is 3 minus 1. So yeah, 3 minus 1 whole square. So ID is 2 milliamps. So we know that ID is 2 milliamperes. Now there is another current that is flowing, which is I1. How to find I1? It is VDD upon R1 plus R2, considering that since there is a coupling capacitor, so no current flows through this capacitor. So this will be 12 upon 20 plus 60K. So that's 12 by 80K. that is 1.5 into 10 to the power minus 4 amperes. Or if we write in milliamperes, that is 0.15 milliamperes I1. So IDD will be 2 milliamps plus 0.15 milliamps. So IDD is 2.15 milliamps. VDD is 12 volt. So power dissipation will be 12 into 2.15. So this is 25.8 milliwatt. Now there is one thing that you need to notice, that the major power is drawn by your MOSFET circuit. The biasing circuit, which is the circuit consisting of this R1 and R2, they draw very less power. So if you are designing, for suppose you are a designer and you have to design the circuit, then what you need to understand is that the current that will flow through the biasing circuit should not be more than 10% of the main circuit. So that means the MOSFET circuit, if it takes like 10 milliamperes, then your biasing circuit should not take more than 1 milliamperes of current. So that's how you should design your circuit. So maximum power should be drawn by your MOS circuit, which is the main circuit, right? So that is one one key point that can be okay. So my point is that here there are two circuits, right? Like if you see from VDD to ground, this is one circuit and this is another circuit. This is what I'm calling as biasing circuit, which is the circuit consisting of R1 and R2. So this biasing circuit should not take more than 10% of your main power. So that means if your MOSFET based circuit, which is the main circuit, is taking 10%, like 10 milliamperes of current, then your biasing circuit consisting of R1 and R2 should not take more than 1 milliampere. So that is the idea.
I had a doubt in this. Hello.
Hello, am I audible?
Yes. So I have a doubt in this. I can't hear you. Not audible.
Not audible?
Yes, audible now.
Am I audible now? Okay, so were you
Yes.
able to? So still my screen is freezed. So I have solved this problem, question number 8. Were you able to see that?
Yes.
Are you able to see the solution for question number 8? Okay, because here I am unable to. Okay,
Yes,
so
it is fine. It is fine now.
actually my screen is stuck. So
Okay.
it's stuck.
Now, what is the disadvantage if more than 10% current is going to the bias circuit?
Yeah. So the idea is, see, you want maximum. So it's more like a wastage, right? Because if your MOSFET draws more power, your amplification would be better, right?
Yeah.
Because you need the significant amount of current for the MOSFET. Now, let's say 50% of your whatever current it is drawn by your this normal biasing circuit, and your MOSFET is drawing other 50%. So this particular 50% is waste, right? You don't need that current over there. So you design it in a way that the current, so because the spec that you get while designing is power dissipation, you have to optimize the power dissipation. We want our batteries to last longer, right? We
Yep.
don't want to charge our batteries every half an hour. So for that, what is the constraint that will tell you about this battery charging thing? So it's basically the power dissipation. The lesser power dissipation you will have, the better battery life will be there. So that's why, no. So we are talking about power dissipation. We are not talking about input power. We are talking about power dissipation. Input power will be much smaller. So input power, when we say, input power is basically the power that comes from input signal. So it's input voltage into input current. So the signal voltage into signal current. So if you use this particular source Vn, and with this if you find the power, then that is your input power. But when we find it from the supply, that is VDD, it's actually the power dissipation. So it talks about the power dissipation of the whole circuit, and it's definitely the larger. So when you have so the limiting power will come from your power dissipation, but your input power will talk about gain, because with input power you will find also the output power, and input power and output power, from there you will find what is the power gain that you obtain from your amplifier. So that is different. This is power dissipation, which is basically uh, so see, we don't use input term for power supply. When we talk about input, it is always the signal that we talk about as input. So when you are, so this VDD is not an input, it's power supply. So that's why, to make things easier, we never call VDD or supply as input DC power or input power or input voltage. We never call it that. We always call it as supply voltage. And whenever there is a term called input, it always signifies to the signal, the AC signal that you give to the input terminal, which basically gets amplified at the output. I mean, it need not be AC as well. So because in op-amps, it is a AC as well as DC amplifier. So there you give DC also as input. But input basically means what you give to your input port or input terminal, if I should say. So that comes as input. But this VDD basically is the supply voltage. So please never confuse between the two. Input is the signal that you give as input, and VDD is the supply voltage. So power dissipation is always calculated with respect to your supply voltage. So what is the supplied power? From there you find out, okay, what is the power that is dissipated by the whole circuit. Uh, Hope this is clear.
Yes, ma'am.
But there should be some power that should be dissipated by the, like, when the signal also flows through the circuit. Is that negligible in this case?
Yeah, it's almost negligible. Why? Because the signals that you will be amplifying. So to be very practical, if I'll tell you, the maximum gain that you can obtain from a single stage MOS amplifier is around 60 dBs. Theoretically, practically it would be even less. So around 50 dBs. And for that particular, like for that particular gain, the swing that you get is very small, the output swing. So for corresponding to that, the input values that you give are very small. They are, most of the times they are in microvolts. So when the voltage is in microvolts, so you can also understand how much the current would be. The current would also be very small. So the power is in micro, like it's very small. So it's a picowatt that range of power, nanowatts, picowatts. So it's always negligible compared to a milliwatt, right? So that's why the power, uh, majority chunk we consider. So that's why the dissipation of power is taken from the supply voltage compared to your input power. But definitely,
Uh,
yeah.
so is there like are there some cases where the signal power is also like as important as the supply power? And like here, supply power is important, but we neglected signal power. But
Yeah.
are there cases where signal power becomes important?
I mean, no, that is not possible. That's what I'm saying because your supply voltage is always very high. It will be either 3.3 volt, 5 volt, 12 volt. It depends. So, supply voltage is what you give to the chip externally, right? So it's always a larger value. You boil down through resistors and everything, but still that value is that voltage is very large, and also the current drawn is very large compared to your input signals. They are, as I mentioned, they are in microvolts, right? So microvolt signal, how much current would it draw? It will, the currents will also be in somewhat microamperes, right? Even if they are in milliamperes, then also still it is very small. So milliamperes, that is not possible also. So they are in micros only. So micro nano amperes of current, and voltages are mostly in few microvolts. So the power contribution of that input source is very small, so you always neglect that.
In case of even like multiple stages as well.
Yes, yes, yes.
Okay,
Because
thank you.
your, yeah, because in case of multiple stages also, your output needs to be defect free, or I should say there should not be any um, there should not be any disturbances or any type of distortion in your signal. So even in case of multi-stage amplifiers, what you do is you have one stage. One multi-stage में the advantage that you basically get is not that your output increases too much. So देखो, अगर if you have your VDD of 5 volts, your peak to peak voltage at output cannot go beyond 5 volts, right? No matter how many stages you have. But what is the advantage that you get in multi-stage amplifier? That the gain increases. So that means your output is fixed, your gain increases. That means you can amplify even the smallest signals. So then the magnitude of input reduces, but output does not change because output cannot go beyond your VDD. So it's more like from output side the things are fixed. VDD is fixed. Now, with increasing gain, what you can do, you can either increase your V out or reduce V in, right? So, what we use is we reduce the V in. So, it's like earlier, let's say your amplifier was able to, so it basically increases the range of signals. So, uh, let's say, for an example, your speaker can take only output signal, the signals which are more than 3 volts, okay, and 5 volts is your VDD. So that means 3 to 5 is the range of signals that your speaker can detect. Now you have amplifier besides it, and you have to give input to it. So your input should be like see, input. How do we write? We write gain as V out by Vn, correct? Now V out is almost fixed. It is from 3 to 5 volts, and gain is there. Now it changes depending on what circuit you have, and then corresponding to that you can get Vn. So if you have a larger gains amplifier, so that means it can basically amplify like smallest signals. So there might be few sensors which are very sensitive, right? And those sensors will have very small peaks, and those peaks needs to be amplified. So those can be picked up by these large gain signals. So the idea is that, so it basically increases your input signal range, if you can understand by that. So the range is different. Like for very large gain amplifiers, since output range is fixed, your inputs will be very small values, like let's say nanovolts or even picovolts. And if it is a single stage amplifier, so it will be in few microvolts. So that's how things change. Is this clear?
Yes, thank you.
Yeah. Okay, so moving on to the next problem. So in this problem, here, okay, it's mentioned that it is a P-channel MOSFET with operating DC bias current of ID of 124 microamperes. It's a PMOS with ID is K, V is G minus mod VTHP whole square. Now you need to work out the values of R1, R2, RS and RD such that the current through the R1 and R2. So let's say I call this I1. Okay, so it is given that I1 is 0.5 microamperes. The current through the MOS amplifier, this is ID, it is mentioned as 124 microamperes. The maximum gain of the circuit, so gain is given, let's say G, it is given that it is -5. So that means, okay, so it's not that straightforward because it has RS as well. But yeah, but maximum gain is 5. This is volt by volt. And the output can swing symmetrically over the largest possible range while maintaining the device in saturation. Okay, so these are the things given, and K, yeah, K is given. K is 3.83 millisiemens per volt. So with these givens, first of all, since I1 is given, so let's find the relation between R1 and R2. So R1 and R2, so R1 plus R2 will be 5 upon 0.5 microamperes. So this is R1 plus R2 is R1 plus R2 is 10 mega ohms. Now you know that R1 and R2 are 10 mega ohms. Any other information VT is given, okay. So VT is 0.5. Now this is 10 mega ohms. For turning on this transistor, VSG should be greater than VDH, right? So this is Vs minus Vg should be greater than VDH. Here Vs is 5 minus the source plane gate. So Vs is 5 minus ID into Rs. And if we write this KVL, we will have 5 equal to IDRS plus VSD plus IDRD. Here I equal to K VSG minus VTH square. Now if we substitute it over here, no, because RS and RD are also not known. So here it will be triple. Yeah. Okay, so ID we know it's 124 microamperes equal to how much is this? 3.38. 3.83 Vs minus Vg minus Vth is 0.5. 0.5 whole square. So from here, VSD can be found out, like it is 124 by 3.83 root under plus 0.5. So this will give us VSG. So how much is this value? So VSG comes out to be 6.18. Okay, so here it is micro, right? Here it is mini. So so micro and mini also needs to be considered. It's point. VSG turns out to be 0.6799 volts. Now this VSG, since VSG is greater than VTH, so this is correct. And now talking about gain, right? So here we see that it's not a straightforward CS amplifier, rather we have an RS over here. So this RS will come in picture by calculating the gain. So let's find out the gain through small signal analysis. So by small signal analysis, if I have to draw, this is source, gate, drain GMVSG plus minus VSG. Okay, this is grounded. So R1, R2. Here it is V in. Now this is source, drain, gate. From gate so from drain there is a resistor connected from drain to ground, and there is another resistor connected from source to ground. Am I audible, everyone?
Yes, yes,
Is my screen visible to you all? Like the
yes,
small signal model that I'm drawing?
yes.
Okay. So my screen is stuck here. Man is a problem. But anyways, you people are able to view, right? The continuous progression is clearly visible to you all, correct?
Yeah.
Okay, then it's fine. So, yeah, maybe recording me there would be a problem, but anyways, so yeah, this is the small signal model, right? So here you have your V in, this is your V out. What you need to find is V out upon V in. So again, V in is VSG over here, it's clearly visible. No, V in is VSG, but negative of VSG, because here you will be applying V in with respect to ground. So it is minus of VSG. So yeah, somebody is saying V out by V in would be minus RD upon RS. So that's correct with all the simplification that is done. So when you try to solve this particular circuit for V out by V in, what you obtain is minus GM RD upon 1 plus GM RS. Now considering GM RS is much larger than 1, we get the gain to be as minus RD by RS. So this is the gain that we know, and it is given that gain is, this is gain. So the gain is minus 5, which is RD by RS. So RD is 5 times of RS. RD is 5 times of RS, and so this particular expression so this can be further simplified to 5 equal to ID RD plus, so maybe we can write it like 6 RS plus VSD. So this is now simplified to this. now, so this is ID. Okay. So the ID that is given to us as 124 microamperes, this is IDC, right? But since it is an amplifier with a small signal V in voltage, so there will be a small signal current also. So that small signal current So the total current that is flowing through this particular circuit is IDC, that is because of the DC biasing, but plus small current ID, this comes because of Vin. So this Vin gives rise to small ID, okay? Now, the total current that is flowing in that particular branch is IDDC plus small ID. This now, as you increase your Vn, what will happen is your small ID reduces. So that is like I told you, right? There was this opposite behavior because of which we get negative gain in the CS amplifier. From that narrative, what will happen is when small Vn, that is small signal input, increases, this will lead to reduction in the small signal current ID. Now the question is that let's say this by reducing, so ID, the small ID can maximum reach to ID DC. The maximum volt current that it can reach is maximum ID DC. So I total is like we are trying to increase the Vn to see that the maximum, what is the maximum swing and the output that we can get. So for that, IDDC, and at this point, our small signal is also reached IDDC, but in negative direction. So it's like if it was the positive peak for Vn, the current we got is at negative peak because of that inverse relation. So here it will be the IDDC again. So this is the condition when maximum input has been applied, so that the input current, the small signal current becomes almost equal to the DC current, but they both are in opposite directions. So making the total current to be 0. Now, if so, this was for positive cycle of Vn, right? Similarly, when there is negative cycle of Vn, it will show the opposite behavior. So like for negative cycle of Vn, your current will increase. Like so for negative cycle of Vn, you will see the positive cycle of small ID. So that means the positive ID. So I total in that case, again going to the maximum, we will get ID DC plus ID DC. So that is twice of ID DC. This is I total. Right? This is for the negative cycle. So with input, what is happening is your this is small ID, okay? Small ID. How it is changing is this is 2 IDC, and this is so this is plus IDC, this is minus IDC. This is when Vn is negative, and this is when Vn is positive. In this case, the I total is 2 IDC. In this case, the I total is 0. So now, in case of IDC plus small id equal to 2 IDC, this is if the current flowing through that particular branch is 2 IDC, and also your transistor, for this particular current, your transistor needs to be in saturation. So that means VSG minus mod VTH is equal to VSD. This is the smallest possible condition. So we know that ID equal to K VSG minus VTH of whole square. So VSG minus VTH is root under ID by K. So IDC plus small id is equal to I total. This is twice of IDC, and from here, if we look into like the total current will be given by K VSG minus mod of VTH whole square equal to 2 IDC, then VSG minus mod VTH is root under 2 IDC by K. This is also equal to the VSD limiting condition, right? The smallest possible VSD. So now if we apply the KVL, so VSD is 5 minus 2 IDC into 6 times of RS. So this is coming from this total current equal to 2 IDC. From there we are getting this. And this VSD, if we substitute this over here, so this will be twice of IDC by K equal to 5 minus 12 IDC RS. So RS equal to 5 minus root under 2 IDC by K upon 12 IDC. So what is the value of RS that we get? Yes, what is the value of RS that we are getting from here? Is it 3.189 kilo ohms? So RS should come out to be 3.189 kilo ohms, okay? Now the follow-up question to this, so this question was question number 9. So question 10, here RD has been asked. So RD is 5 times of RS. So this will be 3.189 kilo ohms. or into 5, so which is 16 kilo ohms. This is RS. Now coming to question number 11. So here we have to find the value of R1. Now considering that 2 IDC condition, VSG minus VTH is root under 2 IDC by K. R1 plus R2 was already found to be 10 mega ohms. So VSG is root 2 IDC by K plus VTH, and VSG turns out to be 0.75 volts. VG is R2 upon R1 plus R2 into VDD, and Vs is 5 minus 2 IDC into RS. Vs, right? RS. So Vs equal to, by solving this, we know IDC, we know RS. From there we get Vs as 4.2064. That is the value of Vs that we get. And from these two, if we find Vg, it turns out to be 3.456 4.6456 volts. This is Vg, this is Vs. So 3.456 equal to R2 by R1 plus R2 into 5. So that is 3.456 equal to R2 into 5 upon 10 mega. 2 mega. So this is R2 is around 6.913 mega ohms, whereas R1 will be 3.08 mega ohms. So is this clear? Any doubts on this? Is this problem clear to everyone? Okay, so we have found out. So the question in the beginning was that you have to find the values of all the resistors R1, R2, RS and RD. So we have completely solved this problem by calculating RS, RD, R1. So basically R1 and R2. So all 4 resistors have been calculated. So if we look into question number 12, so it is like saying that to find the value of R2. So here we can find the value of R2 as this. Also, let's say if we consider here, we considered in the above question considering 2 IDC as the total current, right? Now let's consider IDC only as the total current. We are not considering the small IDC, for suppose small ID. Then what will happen? So VSG minus VTH is root under IDC by K. So from here, VSG turns out to be 0.6799. Vs is 5 minus IDC into RS. So Vs is 5 minus 124 microns into 3.2 kiloohms. So Vs turns out to be 4.6032. Now Vg is equal to Vs minus VTH. So this will be 4.6032 minus 0.68. So Vg is equal to 3.9. 3.923 volts. If this is the Vg, then R2 would be 3.923 into 10 mega by 5. So this is 7.8464 mega ohms. But so by using this, if you want to calculate R1, this will be 10 minus 7.846 mega ohms. So this is 10 minus 7.846 turns out to be R1 as 2.154 mega ohms. So this is the value of R1 that we get, R1 and R2, considering the total current to be only IDC. So from here, if we observe that while considering 2 IDC, the resistor values that were coming out to be were R2 was 6.913, whereas R1 was 3.08. And if we look into the options, we don't find any option over here, right? So considering 2 IDC in this case was not correct because we don't have the option for that. Then when we solved it using only IDC as the total current, we find out that the resistor values are for R2 it is 7.8464, so which is almost like this, 7.8464, and then for R1 we have 2.154. So here we have 2.154. So IDC is the correct result. With IDC we are getting the result. And here it is 16, so it is almost equivalent to this one. And this is 3.189. So RS, this is 3.189. Okay. So is this clear? So we have solved 12 problems today. So are these problems clear? Any doubts and any problems? Okay, so if there are no doubts, maybe we can break over here. You can go through them again. Last two were little complex to understand. Okay, so last two, so it's basically, see, last two you have to find this R1 and R2, right? So you have to find R1 and R2. One relation you know, that is from the I1 current and this 5 volts. It was given, right, that I1 is 0.5 microamperes. From there we found out that I1 and R1 and R2 are 10 mega ohms. This is what we already found out. Now the idea is to find the values individually. So for individually finding the values, we know that Vg is R2 upon R1 plus R2 into VDD. So here, if Vg is known to me, then I can write R2 as Vg into 10 mega upon VDD, correct? Now, here we know that VSG minus VTH is root under IDC by K by the saturation equation. So this is basically IDC equal to K VGS minus VTH whole square. So from here we get this. Now you know the value of IDC, you know the value of K, you know the value of VTH. So you can find VSG, correct? We also know that VSG basically means VS minus VG, right? So now since it is Vs minus Vg, so from here if I find Vg, I can use it in this particular equation to find R2. So how to write Vs? This is S, this is D, this is G. So I want to write the equation for Vs. How would I write? So it is basically whatever the drop across RS, if we remove that, the remaining voltage is Vs. So that's why 5 minus IDC into RS is Vs. Now you already found out RS in the first problem of this set. IDC is already known. From there we find that Vs is this much. Now since Vs is already known, then we can find Vg. Correct? So by this we find the Vg, and the Vg value turns out to be this value. So when Vg is this, then we can simply substitute Vg over here to find the R2, and that's what we did to finally get the value of R2. And once R2 is found out, we can find the R1. Is this clear? Any doubts? Okay. Anyone else? Any doubts?
Ma'am, I had one question, but not related to any of these problems
Okay.
regarding this course.
Okay.
I started this course a little late, actually from today itself.
Acha.
So the videos I will cover it. That is not
Yeah,
an
yeah.
issue.
Right.
But I was not able to submit the assignments so far.
Yeah, right.
So if I register for exam today, will that be sufficient enough to get my certificate? If I rest of the things, if I do,
I mean, for passing, you need only 50%, right? How much is it for passing marks?
but it includes pass mark for both the things, assignment and
How much is it for assignments?
25 exactly. I do not remember right now, but something like
So
that.
the clear division of marks, grading policy, everything is there
Okay.
with the course. So
Yeah,
maybe
that
you
is
can
there.
look.
Only thing is, I have missed some assignments so
Yeah,
far.
yeah, I understand. So you have missed some assignments. So
Or do I
I
have
guess
option to
3 weeks.
submit them in the coming week? If I submit them, will that be acceptable?
I don't think so because you can see the solutions of the assignments now, right?
Okay,
So now after getting the solutions, if you submit, it doesn't make any sense, right?
I got
So
it.
I guess you must have missed 3 weeks, right?
Yes, yes.
I mean, I guess it should be fine
Okay,
if you get all other assignments done. But maybe you can check through the policy once,
okay,
and yeah, you can then register accordingly. But it should not be a hurdle because there are 12 tutorials, like 12 assignments. Out of them,
okay,
if you don't answer three, then also you should be able to pass
okay,
that particular portion. Yeah, yeah, it won't
okay.
be a trouble. So meanwhile, you can go through the lectures as they are already
Yeah.
uploaded, and these problem solving session is already uploaded on YouTube, so you can check those links as well.
Apart from this kind of sessions, if we would like to share some mails with you or connect with you over mails, will that be possible?
I mean, yeah, you can connect with me, but if you have some doubts, maybe you can bring up in these sessions itself, so it will be beneficial for others as well.
Yeah, yeah, we will do that.
Yeah,
Uh,
yeah, so it will be beneficial for them, and having a two-way interaction while solving a problem is better rather than um, me just giving the answer. So that's why. But yeah, you can connect with me. I have so my email ID is already mentioned. So every PDF will have my email. So this is my email ID. You
okay,
can connect here. Yeah.
okay.
Okay. So if no further doubts, maybe we can uh, just stop here, and we'll take up next problems in coming sessions. So please go through these questions once again. Just in case if you don't understand anything, you can ping me in the YouTube comment itself, or you can like ask that doubt in the next week session as well.
Okay.
And thank you, everyone. And before we sign off, I would like to wish all of you happy Raksha Bandhan. And thank you so much for joining. I didn't expect people to be joining on such occasions, but thank you so much for attending the session. I'll immediately upload this lecture on YouTube, so you will be able to get this particular session within like an hour or two. So, and also I'll post this PDF manual as well, if, like this particular solutions PDF, for you to go through them again.
Thank you, ma'am, and happy Raksha Bandhan to you too.
Thank you.
Just a compliment for you
Thank you.
studying this. Oh, shit.
Thank
Ma'am, are
you.
you there or you left?
Hello.
You're there?
Yeah, yeah, I'm there.
Yeah, okay. So I'm studying this subject after almost 10 years. And
Okay.
yeah, so, but you explained very well. Thank you so much.
Thank you. My pleasure. Okay, so if anybody has any doubts, maybe you can stay back, else all of you can just sign out. Thank you, everyone. Let's meet next week again with new set of problems.
Yeah, thank you.
Thank you. Thank you, you too.